Hello, so we've been looking at the basic symbols that constitute the language, the symbolic language for mathematics, and we've been looking at the different examples for putting these symbols together for expressing statements, mathematical statements that correspond to statements stated in the ordinary language. And now it's time for us to start looking at how we compose proofs, where just to remind you very quickly, a proof will consist of a sequence of lines, where each line is a statement of the kind we've been looking at how to compose, and eventually this sequence should start out with an empty line, and eventually it ends with a line that represents the final goal, the thing we want to prove, the theorem we want to prove. Just one remark though, that some of these lines will be assumptions and some others will depend on those assumptions, and then we use these brackets for representing these. So eventually a proof will look like this, with these lines structured in brackets. Okay, so our starting point actually will be the very last line, because that last line in a mathematical proof structured in bracket notation represents the theorem we want to prove. So let's start with an example. For example, suppose we want to prove that for every number x, there exists a number y such that x plus y equals 0. So some very basic fact that we know is true, and hence we should be able to prove it, that every number has this property that there is another number, so that sum is 0. For number 5, this will be minus 5. For 7, this will be minus 7, and so on. So we know for sure this is true, right? This is a part of very basic knowledge of arithmetic. Now, when I write something like this down, the first thing I should clarify is which language are we using. Remember, mathematical language has core symbols, but then in each given scenario, we might have additional symbols. Like here, for example, the symbol that's not standard throughout all the languages of mathematics is this one. So that makes the language more specific than just a general language. And so we need to know which language we're working with, and moreover, we also need to know what the axioms are for our language, for our theory, rather. A theory is a combination of the language together with the axioms and all the theorems that can be proved in there with those axioms. And so we need to know that, because if we don't know what the axioms are, then we're not going to know what basic facts we can use. And we also need to kind of describe the language and in order that we can get an intuition as to what we're talking about. In this case, this formula, we are seeing that formula as a formula in the language for arithmetic, where the variables will represent numbers. And let's be more specific. Let's say we are working with whole numbers. So this includes the positive natural numbers as well as the number 0 and the negative whole numbers, minus 1, minus 2, and so on. Okay, now we're not going to identify what the axioms are. This topic of separating the axioms for arithmetic is a subject of its own, and there's no way we can fit that into one video. It actually wouldn't even fit into 10 videos if we really thoroughly explain all the ingredients of that topic. So what we're going to do instead, we're going to rely on our common sense for arithmetic, and whenever we use some feature of arithmetic, which we're not going to explain further, we're going to say, okay, let's say that this was given as an axiom. Okay? Great. Now, let's see how we could structure a proof of this statement. So this is, remember, this is the last line. This is where we want to arrive to at the very end of our logical conversation. And we might be thinking now, you might be thinking now, okay, where do we start? Well, starting point is always easy. You always start with nothing. You start with an empty line. Okay, then the question is, what goes next? Now, just as every mathematical statement, like this one, is composed out of pieces which are kind of glued to each other in a hierarchical manner, we will go according to that hierarchy. So what I mean here is, if I insert invisible brackets, that this sentence, and I think we've touched on this topic earlier as well, this sentence is structured in such a way that the last logical operation we are applying is for all x. And so it's first we've got for all x, last or first depending on whether you read it from inside out or outside in. So there is for all x, right? And then inside there we've got there exists y, and then inside there we've got equals. And then inside equal we have two sides of equal. So on one side we have x plus y. In other words, we have plus, and inside that we've got x and y. And on the other side we've got 0. So let's actually map this structure out so that we can recognize it in a more visual way. So the formula starts with for all x as the outside ingredient, and every time I'm going to go inside the formula, I'm going to make a line or maybe an arrow going down like that. And then the next logical operator, so this logical operator of for all x is being applied to whatever comes inside the formula, and that thing inside the formula itself has a certain logical operator applied to something that's even further inside the formula. And so if we go along this way, then in the third layer we encounter equality. And so remember, equality has two inputs that it should take, and so it will branch out like this: the thing that's on the left hand side of the equality and the thing that's on the right hand side of the equality. And on the left hand side of the equality we've got a plus, right? And the plus also has two inputs, so that will branch out further. And so we've got here x, and that doesn't branch out further to anything. And we've got y. And on the right hand side we just have 0. Now it is important to note here that these nodes of this graph that we just constructed, these nodes are of two different kinds. Some of these nodes are nodes that represent objects, and others are nodes that represent formulas. And remember, what's the difference between these? So object is, in the case of this language of where the variables represent numbers, objects are the whole numbers, and formulas are statements we make about them. So one way of thinking about this is that when you've got objects, you never ask the question whether the object is true or false, but when you've got some formula about them, then you can ask your question, okay, is that formula true or is that formula false? A formula is seen as a kind of statement, a mathematical statement that is being made about those objects, and then you can ask yourself, okay, is this true or is it false? But when you just have an object like x plus y here, that's an object. You don't ask whether x plus y is true or false. That doesn't make sense, right? So these objects are called terms, as we mentioned a few times. And so I'm going to now color these with this special color here to represent the terms. So they are terms, x and y are terms, they represent objects. X plus y, which is represented by this node, is a term as well, and 0 is a term as well. But equality is no longer a term. Equality is a formula, because equality can be true or false, right? And so let's use a different color for that. Let me use something of this kind for representing the formulas. There we go. Okay, now this tree that we created which kind of gives us the hierarchical structure of the formula, will now be used to lay out a framework which we should apply in order to structure the proof of this statement. And at each step that we're going to make, right? Each of these steps is going to be aligned with intuitive logical understanding of what the statement says. And it's very important to keep this alignment in your mind so that you never make a step on your computational side that logically you can't interpret the meaning of that in an intuitive way. Okay, so, and in fact, we're going to use the intuition to guide us how to structure the proof as well. And so if you already have a very refined intuition for these things, you might be able to rediscover on your own how the proofs can be structured without listening to what I have to tell you. So let's look at this statement. What does this statement say? So I'm now trying to look at the intuition of it, right? What does it say? It says, for every object X, something happens. And look how I kind of disregarded this whole thing. I just called it something, right? I'm performing some kind of abstraction where I don't care at this point, what does this say? What I care about is that for every object X, that thing should happen. So on my directed graph, what I'm really talking about here is that the statement is of this kind, where the last logical operator that was applied was for all X, and it's applied to some object, which is this whole thing, right? And before we unpack what this statement is, I shouldn't actually have called this object, I should have called it a statement rather. Before we unpack what this statement says, let's just fix in our mind what is happening here at this arrow when we transition from the first node to the second one. So what we're saying here logically, without going into what the rest of the formula says, is that we're saying here that for every object X, something will happen, something should be true. So for every number X, some property should hold for that number. That's what we're saying here. And let's not worry about, at this point, what exactly that property is. Why not? You will see in a moment why not. So what we want to do now is to ask ourselves, if I were to prove that for every whole number X, some property will hold, how would my proof look like? Well, it depends on the property, right? Yeah, it does depend on the property, but there is some part of the proof that does not depend on the property. And this part can be written out, and it can be fixed like that without changing it further, as we're going to go and unpack the property itself. And so let me show you what that part is. So because we want to prove that something is true for every X, we're going to assume that we are given X, and we can just write an X there to propose this as an assumption. But because it's an assumption, I want my bracket already to start opening up here. Remember, the bracket opens up whenever the line is an assumption. And what I want to do, I want to take a series of logical steps to eventually come to the conclusion that that is the property that we're trying to establish for X. So in other words, this ingredient here. So I want to start out with a random X and arrive to this conclusion. So now at this point, it's very important to listen to the logic or the story of what's going on here, right? So we are starting out with an X. We're not giving X any specific value. Why not? Because there are infinitely many numbers. If I started checking that property for each number separately, one by one, I would never be able to finish. So because I'm proving something for infinitely many values, or maybe for a large enough number of values, even if it wasn't infinitely many, I actually don't want to be specific about what X is. Rather, what I do, I imagine that X could have been specific without specifying X and work with this general X instead. And if I manage to prove something about the general X without any attribute of x, right? Any specific attribute of x, then surely if I had a specific x like x equals 5, I would have been able to do the same proof just by replace the x I will use in the general proof with that specific number 5. And that's what we're saying here. We're saying here, let's assume that we are given an x, and let's see if we can prove without knowing anything more about x than just the fact that it's a whole number, because all the variables are supposed to represent whole numbers. So without knowing anything more about x, let's see if we can get to this conclusion that x has this property that every number should have according to this statement. And what we've done now, okay, is something very important. What we've done now is that we managed to get through this formula. So we've kind of covered this part in a way. So eventually we would want to cross out everything, and once everything is crossed out, we will have the layout of our proof. Okay? So we no longer have to worry about for all x. Whatever I'm going to do here, right? If I can do something here that will logically lead me to this assumption, to that conclusion, then after that, because I've assumed that I'm given an arbitrary x and concluded that, then I can further conclude when I step out of the assumption, I can further conclude that for every x, that thing that I wanted is true. So in my proof, I no longer have to worry about for all x. And that makes our sentence, the statement that I want to prove, shorter, right? Now we have to prove, with this assumption, we have to prove this. You see, in the beginning, I had no assumptions. Remember, I had my first line to be empty line. So without any assumptions, I wanted to prove this. Now I've split this thing up, the thing I wanted to prove, into an assumption part and the to be obtained conclusion part. And so now the conclusion part is shorter because the assumption part has been removed from it. And eventually this conclusion part will become shorter and shorter and shorter until eventually it doesn't have any length, which means that we've proved our statement. So that's the way this bracket proof structure works. Okay, now we go in the next step. Now we're going to see how we can get to this thing. So basically what we're trying to do now is something similar to what we did before, except that now our goal is no longer this. We already know how to arrive there as long as we can arrive here. If I can arrive to this line, I already know after that I can arrive to this line as well. Why? Because I've assumed arbitrary x is given, and with that I was able to arrive to that line. Okay? So now let's see how we can get to this line. And you see, as we compose this proof, we're kind of working forward and backward at the same time. So we've inserted the very first line of the proof, except the empty line. We've inserted the very first line in the proof, and now also a line at the bottom, and now we have to fill the space in between. Okay, so let's see how we can get to this line. We now want here to prove that there exists a y such that something will happen. And again, I don't care what that something is. For now, I don't care, because what I want to do now is to get through this node here on the graph, okay? I eventually want to be able to do this as I did in the previous case, to do this, okay? So at this point, I'm focusing only on the there exists part. I'm not focusing on exactly what property this y that should exist should have, right? Okay, so I want to prove that there exists y such that something will hold. How would such a proof look like? Now, if I ask you to prove that I have a friend who can speak Russian, right? In order for you to prove that, or for me to prove that to you, I would have to bring you a friend, show you a specific person that I can prove to you that is my friend, first of all, and then I can also prove to you that the person speaks Russian. So we need to find this specific Russian friend, or anyone who speaks Russian, if I want to prove that I have such friend. And so exactly the same works here. In the mathematical that exists, we actually want to name a specific y. If we can name it in a suitable way, then we will know that it exists. So we're going to name the y. We're going to assume that y is something, and we still have to insert this, fill this space in. We still have to name the y. We don't know yet because we're not thinking about this property yet, x plus y equals 0. I don't want to go into that right now. I'm going to leave it like that for now. So I don't know exactly what property of y I'm looking for. So I'm just going to name a y. In the future, at some point, I will come back and fill this space. And once this space is filled, it should be named in such a way, y should be named in such a way, that for that named y, I will be able then to prove that x plus y equals 0. And as you see now, what's happening is that the formula to be proved is becoming shorter still, right? So now we've passed through this node. We still have to fill in the space, so we haven't completely passed through that node, but at least we don't have to worry about the exists y part. We just need to know that we have to fill this space and then all the rest of the space between those lines here, the one that I marked with yellow. Okay, so we no longer have, right? We no longer have any of the, we still have equality to prove, but no other logical symbols, right? And so this is where we start now thinking more concretely. So now we are actually going to look at what the formula says. So this is the this ingredient, which now only has one logical symbol to start out with. And so there is no more kind of automatic algorithmic way to pass through this like we've been passing through the first two nodes. This is where we have to look into this statement, x plus y equals 0, reflect on what it says, and ask ourselves, if I'm given x, how can I find a value for y? What should y equal to so that x plus y will equal 0? And as soon as I ask this question to myself in the way I have done now, immediately my mind tells me, wait a second, we can take y equals minus x. So we said that we know basic arithmetic, so we know that when we have a number, we can take minus of that number, right? And so that's what we're going to do here. We're going to take y equals minus x. Now I have to confirm that x plus y equals 0. Well, we just substitute and that's it, right? Okay, so what do we mean by that? We want to now make the next line, which will be a valid logical step, right? A valid logical conclusion from the previous ones. You could say already this one is the valid logical conclusion because when you substitute y in the place of minus x in the place of y, you get x plus y equals 0. But we can nevertheless further decompose this into one more middle step. Namely, we could say x plus minus x equals 0. And this is something we know from the axioms that we would have introduced for arithmetic. Remember how we said that when we need some basic fact from arithmetic, we will kind of assume that we've already introduced an axiom for that. So it's a very basic fact in arithmetic that if you take minus x and you add that to x, you will get 0. And after this, so this line is not a logical conclusion of these two specifically, rather it's a conclusion of one of the axioms. So you're allowed to write in the conclusion line, you're allowed to write anything that either follows from the previous axioms previous assumptions like these, or assumptions or conclusions, doesn't matter, in this case both were assumptions, that it follows from previous lines or it follows from the axioms that have been specified before we start proving theorems. Okay, so that's how we get this line. We get this out of one of the basic properties of arithmetic. And now we can say, from this line we can get to the next line. How? By substituting, in the place of minus x, we substitute y, because since they're equal, they're supposed to represent the same object. And so if I replace minus x with y, this formula, no matter what it says, it should still be true, because I've not really changed it. I've just replaced one name with another name, but they both represent the same object, so I haven't really changed my formula. And the proof is done. Now, when we finalize the proof, in order for us to make it easier for the reader to understand how we got things, right, it is useful to number the lines. So let's number these lines. 1, 2, 3, 4, 5, 6. Of course, we can only, and we can think of the empty line as the line numbered 0, which we will never write. So, of course, we only know how many lines there are once we complete the entire proof, because we're kind of inserting lines in between at every next step, right? That's one thing. Now, another useful way of reminding the reader how you got these steps, I mean, numbering doesn't really help, right? We want to give a bit more information here, and that is, for each line, in brackets, you put a reference to those lines which were used, or if something else was used, what was used, basically, you put the information there. Like for number 1, we didn't use anything because 1 wasn't really a conclusion, it was just an assumption, so we don't have to write anything here for that line. For number 2, the same story. For number 3, we used one of the axioms, so we could say axiom. And if we knew exactly which axiom it is, we could give a reference to that axiom by giving a number, axiom 5 or axiom 7. Then line 4 was obtained by means of lines 2 and 3 only, right? Only 2 and 3 already give line 4. We don't have to think of anything else. So we could put in brackets here for the line 4, we could say 2, 3. And what about line 5? Well, to get line 5, we need to show that, I mean, this is how we set this thing up, right? To show that there exists a y, we need to assume that y has a certain value, to give a value to it, and eventually be able to conclude that. So we actually get it from all the lines ranging from 2 up to 4. So we can write it like this, 2 to 4. And for line 6, this of course follows from lines 1 to 5. And now we have a proof. So this is the proof, right? With a bit of extra information that will help the reader to figure out how were the logical steps made. Because these steps, the one that we made in line 5 and line 6, are kind of automatic steps, we will always have those steps made when we want to prove something that starts with exists, or something that starts with for all. We might actually drop these references. So for a reader who is already familiar with these kinds of things, and just keep these, unless of course the reader is also quite well familiar with arithmetic and so on, then we can drop everything. But the idea is that imagine when you get lots of lines here, then you might struggle to see exactly which lines were used to get to line 4, and so it's useful to have references like this. Now you see how different this is, what we've displayed here, how different this is to what you would have gotten with your standard kind of school type of approach to mathematics. Where you would have probably written the following. So imagine you know the meaning of quantifiers, so you understand that this thing says for every x there is a y such that x plus y equals 0. And then probably what you would have done after that, you would have written, okay, I want to find a y for a given x. So it's like solving an equation, right? So for a given x value, I want a y value, so I want to express y in terms of x. And then you, for instance, you subtract y from both sides, and you eventually get, or you subtract x from the both sides, and you eventually get y equals minus x, right? And so you've kind of solved your y, hence proving that such y exists, because you were able to solve the equation. But you see how different this is from the actual proof. Because here, the order is completely different, right? Here we have first y equals minus x, then x plus y equals 0. You see? Here it's the other way around. So there is a difference between computing something and proving something. We use computations to come up with ideas of how to prove, but very often the proof is reversed to the process of computation, like it was here. And indeed, when we had to find this value here for y, remember we had a question mark there. And so we asked ourselves, what should y be so that this, and on this side we might have done this computation, right? So in some sense this computation does reflect the fact that I wanted to reach here by a suitable value of y. So I did first consider this and then consider that. But when I lay them out in the proof, first that appears and then the other one. Because logically, the idea is for us to have a sequence of lines where every next line is a logical consequence of the previous lines. And the fact that y equals minus x is a logical consequence of x plus y equals 0, that is irrelevant for us. There are many other logical consequences of this. For example, I could write here any true statement about y, it would still be a logical consequence. What is relevant here is that we can go backwards. What is relevant here is that when y is equal to minus x, then we can conclude that x plus y equals 0. And when we solve equations at school, usually the steps are such that it's always reversible. So we will forget about the reverse direction, which is actually more important than the forward direction given by the computation. But it's the reverse direction we're interested in here, because we actually want to know that when y equals minus x, then this will happen, and not the other way around, even though the other way around is still true. Okay, so that's it for this example. And since it's already a 30-minute video, a bit more than that, I think that should be it for this video. So what did we look at? So just to summarize, what did we look at in this video? We looked at taking a theorem that we want to prove, and now let's actually give this a more mathematical presentation where we are going to state the theorem. So this is the statement of the theorem. We can call this a theorem. So we put theorem right here, THM to abbreviate theorem. And then this is the proof. So there could be colon or there could be full stop, doesn't matter. And so we've got a proof that's here. And so then the lines can be numbered as we did. This is not part of the proof. This is more for the reader to get help in understanding the proof. And since I moved the other thing down, I should also move this one down. There we go. And so we've looked at in this video, we've looked at an example of how to present a theorem together with its proof in the bracket notation. So you write out the theorem as a mathematical statement, then you start its proof, and then the proof has this format with line numbers and indications of which non-trivial consequences when the consequences are non-trivial in some sense, from which other lines do they follow. And then we also, in this example, we had a chance to look into how we could come to the conclusion that something is true for every x, or how we could come to the conclusion that something is true for at least one y, right? Then we also looked at the underlying graph, the directed graph that kind of underlies the, by the way, a graph like this is called a tree. The tree that underlies the structure of the statement of the theorem we're proving, and how kind of laying out the proof corresponds to moving along on this tree and eventually cutting some bits off, so we have a more elementary basic part, and then using the axioms to come to the conclusions given by those basic parts. And also we looked at how important it is at each step of moving from one node to the other on the tree. So in the formula, moving moving towards the inner and inner part of the formula, at each step how we are focusing on that specific step, and we're not really caring too much what the inside of the formula says for the time being. Like when we were dealing with for all x, we didn't really care at that point what this said, and we laid out for all x proof without caring what that said. And then after that, we now wanted there exists y proof, so then we focused on there exists y. We didn't care what x plus y equals 0 means, and so on. Okay, and that's it for this video.